Are we on?
Yeah.
Hi, everyone. Let me just calibrate a little bit. How many of you are working for space industry? Okay, that's none. Then it's gonna be quite interesting for you, I hope. I guess as you know, recently space missions have been increasingly attacked by the adversaries. Most of the discussion, however, revolved around space segment. And it is our argument that it is the ground segment that is more likely to be targeted by the adversaries instead. And that is because of the attack surface it imposes. So in this presentation, I will briefly compare the space segment with the ground segment from the attack surface point of view. I will then give you some short introduction to the SLE protocol and its security aspects and vulnerabilities. And then I will show you a couple of demos how we can abuse those security issues. And then also I will finish with some mitigation techniques. So every space mission can be loosely divided into two segments. It is a space segment, and then it is the ground segment, which also includes the user segment, the end users. Usually space segment is very complex. It consists of, let's say, a space asset, which has many interconnected elements on board of the spacecraft. However, if you think about it, it is just like one, it is just like one entry, it has just one entry point, because it is just like a one element in the system. So because of that, it presents a very small attack surface. There is only one in and one out. And on top of that, the communication with the spacecraft can be quite challenging. And it's not because of the technical aspects of it, but rather because of the environmental aspects, like the distance from between the ground station and the spacecraft, the visibility, the orbit, and so on. On the other hand, the ground segment is of much less complexity, but there are many interconnected components with which communicate to each other, either by sending the input to or receiving the output from other components. And on top of that, there are many potential entry points, because of which it presents much larger attack surface. Additionally, there is no sophisticated equipment required to hack into the ground station, because this is just a standard infrastructure. And the last point is that there is a lot of software that is on the ground segment. Many applications, however, are custom builds, which presents many additional avenues for new vulnerabilities, because it's not a standard software which many people have used before and tested it. So on this image, you can see at a very high level breakdown of a space mission. From right to left, you have a space segment, which consists of a space asset or multiple assets. In this case, it would be a spacecraft. And on the left-hand side, you can see the whole ground segment. So as you can see, there are many more components into the ground segment. There is a ground station which communicates to the spacecraft. There is a mission control which talks to the ground station, and it is used by some users connecting to the mission control system, either from internal network or through the internet via VPN or jump host or whatever that organization might have. So the point I'm trying to make is that it's going to be much easier to hack into this thing and try to hack into the spacecraft through it rather than build it yourself. So Now about the SLE. SLE is a standard, it's a protocol that is developed by CCSDA standardization body. And SLE is basically lets the users to send the telecommands to the spacecraft and receive telemetry from the spacecraft. It is based on the TCP/IP. It supports transport, encoding, and authentication. And it can have two roles, SLE provider and SLE user. Now, SLE provider is a ground station from a high-level role perspective, and SLE user is something that is communicating with the ground station, which usually is a mission control system. So in a nutshell, SLE defines a protocol for transferring PDUs using the TCP/IP for data transfer and ASN1 notation for data encoding. So in the system, you can see that it is, just from context, it is the link between the mission control system and the ground station. Now, here you can see all the organizations and companies that are responsible for SLE and CCSDA standardization body in general. You can see most of the major players there. If you look at the documentation, you'll also see that there is quite a few member agencies responsible for the standard. And later down, if you see, if you look at the actual PDF, there is 3 times as many other private and public corporations involved in the standard, either development or they use it. SLE is also present in most of the specialized equipment that is running on the ground station, like in this case, the Cortex, Safran Cortex ground station equipment. And here, just also for a reference, NASA Near Space Network lists SLE as one of their interfaces and capabilities, which basically means that almost everyone is using SLE internally on the communication between the MCS and the ground station. Now, for the purpose of our research, we focus on something that is called FCLTU. It is Forward Communication Link Transmission Unit. And it's basically the thing that lets you to send telecommands to the spacecraft between the MCS and the ground station. It defines a bunch of, a decent list of operations at the protocol level. However, for us, we are focusing only on the following ones, which is the bind, unbind, start, stop, and transfer data. And later you will see why. So, if you look at the documentation, there is basically no privacy. Also, the data integrity is lacking. There is a sequence numbering to attempt to prevent operation injection at the protocol level and potentially seizing the control of the spacecraft, but there is a very easy way to bypass it. And also there is an authentication mechanism, but because there is no encryption, it's very prone to replay attack and capturing the credentials and then reusing them. So our testing environment is extremely simple. This is assumed breach attack scenario, so we are assuming that the adversaries are in the network. And it consists of 3 elements. SLE provider, which plays the role of a ground station and runs on a typical Debian machine. For that, we use, for the SLE side, we use the ESA implementation, European Space Agency implementation of SLE. On the user side, we are using the role of the SLE user is played by the mission control system. And for that, we use the Python SLE implementation, which just happens to be implementation done by Vision Space, which is our company. And this is just to demonstrate that it doesn't matter which implementation you use, as long as this implementation is following the standard, your mission is going to be vulnerable. And then, of course, we have a Kali VM in the middle, trying to mess things up. So, from the technique overview point, because there is no encryption, we thought that the best idea to demonstrate the attack, to come up with possible attack scenarios, is going to be to use man-in-the-middle attack. So at the high level, we do the ARP spoofing. We capture the data at the TCP frame level. We decode the ISP1 frames, which I will explain later what they are. But they basically carry the CLTU data, which is the thing that goes to the spacecraft at the end. And then we update those frames and push it forward to the ground station. I guess most of you know how the ARP spoofing works. So we basically poison the ARP tables between the two nodes, which is mission control system and the ground station. We put the packets in the NFQ filter for the processing, and the processing is actually where the fun starts. So once we capture the frame, they contain the SLE PDUs, which are in the ISP1 format. We extract them. ISP1 is using ASM1 encoding, so we decode the standard type, length, and value fields. There are a few custom fields and context-specific structures and sequences. So it's going to take a little bit more time to figure out what they are, but because of SLE comes with a relatively nice and complete documentation, it's not going to be that difficult. And as I mentioned before, we focus on the CLTU only. So once we capture the data, we have to map it. Once we extract those values, we have to map it to the FCLTU data type specification. And so here is an example. This is one of the frames that contains the CLTU bind data. What you see is a route-based stream. It consists of the ISP1 header, and then the main structure, and then everything else is CLTU bind specific fields. One of them being the CLTU bind invoking credentials. It is not encrypted, so anyone on the wire can actually decode it. Okay, so finally now it's going to be demo time. Before I show you some demonstrations how to exploit this protocol, I'm going to give you a demo of how the standard communication between the ground station and the mission control system looks like, just so that you understand the baseline. So first we're going to establish the connection using the CLTU bind. Then we're going to initialize some of the services at the ground station. Then we're going to transfer some data. We're going to stop the service at the ground station, and then we're going to unbind from the ground station. So let me see if that plays. So here on it's a recording. So on the bottom side there is SLE provider, which is a ground station, and on the top side there is a SLE user, which is a mission control system. So I have prepared a small routine where we start the SLE provider, and then we start the SLE user. Let me pause it for a second. Where we just connect, do the bind, then we start the invocation where we set up the ground station, then we send some data, we unbind, and then we disconnect. So that's basically how the communication looks like at the high level between the mission control system and the ground station. So there are a few things we can do about it, and we have prepared I have prepared a couple of demos where I can show you how we can actually abuse this mechanism. Since there is no encryption, we can capture the credentials, and we can generate a little bit of denial of service. This is going to be in particular annoying for the users because if we start changing the credentials on the wire, the users won't be able to authenticate to the ground station. And the reason why it's extremely annoying for the users is that because at the protocol level, there is no feedback from the ground station coming back to the mission control system. So the connection is gonna be just dropped, which means that the users will try to connect, but they will fail, and they will never know why. They will have to run investigation on the ground station to then understand why they are failing the connection. So what we do here, we just capture the frame, we mangle with the authentication bytes, we put whatever we want, and then we forward those frames to the ground station, preventing the authentication. So the setup is pretty much the same, except that on the left-hand side we have our exploit that is running on the Kali machine. So first we're gonna start the exploit, and then we're gonna proceed with our routine as before. So once the exploit is up, we start the ground station, then we start our mission control system. We try to bind, and then we see that we didn't get any feedback. However, the next request is failing because of the weird state that the mission control system is in. And the only information is on the ground station that the user has failed the authentication. Otherwise, the connection is dropped and there is no feedback. So the users have no idea what is happening. So, since we have access to the credentials, we can of course also capture them and display or save for later use. So that's what this demo is going to be about. So we start our exploit, and again we proceed with the same routine. Except this time, the whole operation is invisible for the users. They proceed with the authentication as per nominal. They send some data and then disconnect. But you can see that on the left-hand side, we actually were able to capture the credentials. And in one of the later demo, you will see how we can actually abuse that and reuse the credentials to take over the SLE session. So it is very tempting to start tampering with the data. If you know what spacecraft is expecting from you, you can capture the frames, and then instead of playing with the SLE operations at the protocol level, you can start playing with the spacecraft itself. So for that, you just have to grab the frames which contain the data transfer PDUs and replace the content with your own. So in a similar setup to the previous one, except that on the top side there is our exploit. We are gonna be sitting on the wire looking for or filtering for those for that byte string, which is bytes from 0 to 9, and then we're gonna replace them by a byte string of our choice. Like in every example, we just use byte 41, which is ASCII representation of letter A. And then on the left-hand side, at the bottom, you have our SLE provider, which is ground station, and then on the right side, there is mission control system. So the exploit also tells you a little bit what you are doing. So once it's up, we can proceed with the exploitation. So we start the ground station, and then we start the mission control system routine. So we connect, we send some data. You can see that we have sent bytes from 0 to 9. On the left-hand side, you can see that we have captured those bytes. This is the last bytes of the frame. And then also at the bottom, you see that the spacecraft actually has received okay, I was trying to play it again. you can actually see that instead of bytes from 0 to 9, we have received the bytes, 10 bytes of 41. I cannot really pause the video. I don't know why it's not pausing, but I just want you to show. I just want you to see it again. Okay, so this is the moment when we send it, and you can see on the left side you have 41, 41, 41, and so on. So this is what was received at the ground station, and effectively it's going to be forwarded to the spacecraft by the ground station. So if we put all those elements together, we can actually try to take over the whole SLE session. So what it means is that we first are going to prevent the users from authenticating, so that they cannot connect and establish the session. We are grabbing the credentials and reusing them for our own SLE session that we are going to establish to the SLE provider. And once we have done that, we can actually start communicating with the spacecraft directly as if we were legitimate mission control system. So on the left-hand side, you see there is exploitation part, and on the right-hand side, there is, again, the same setup with the mission control system and the ground station. So we start our exploit. We start the ground station, then we start the mission control system. We capture the credentials. The user is unable to proceed with the communication because there is an exception at the ground station, and we just reuse the same credentials and establish our own session to the ground station from our Kali machine. And we can proceed with our routine of setting the bind, setting the ground station equipment, sending the data to the ground station, and effectively to spacecraft. And then we can proceed with unbind and stop and unbind, as if we were the legitimate mission control system. So that's it for the demos. What you just saw is just one of the examples how you can abuse the protocol in order to take control of a spacecraft. As I said, in our research, we focus only telecommanding part because we wanted to demonstrate that you can actually take over the control. But there is also telemetry coming down from spacecraft to the ground station, which can also be of use for adversaries. So it really depends how much of impact you want to have for a mission. This is done in a very stealth way, so you can be in the network. If you can be in the network for long enough, you can use that to figure out how the spacecraft communication works, how to communicate with it, how to command different elements at the spacecraft, and then you can use SLE to send your own telecommands. This knowledge might require some of the spacecraft operations knowledge. However, everything that you have seen on those slides can be gathered using OSINT. So all that information you saw is a public knowledge. You just have to be stubborn enough to look around and have enough time to use it, right? But it's out there. It really is. So CCSDS came up recently with SDLS, which is Space Data Link Security Protocol. However, it is done only on or it is implemented only on the link between the ground station and the spacecraft. It is not used yet, so as of now, most of the communication is still unencrypted for most of the missions, especially the ones which are running right now. However, they come up with this. So that said, the link between the mission control system and the ground station is still insecure, because there is this assumption that is internally in the network and no one has access to it, which obviously, as we know, it's a false assumption. And our idea was that instead of trying to work around and hide behind the firewall, we should implement CCSDS PKI concepts, which already they have developed that at the standards level, in order to enable the TSL-like features at the ISP1 encoding layer. That would basically encrypt the whole communication on the ground between the MCS and the ground station. So the future work is that currently we are trying to agree with European Space Agency to get access to one of their actual ground stations, which we know that they are running Cortex devices in order to see whether we can actually reproduce it at the real hardware. So we are already discussing this with them. This research has recently been picked up by NASA, and they have contacted one of the US companies, and they are pushing for changes to the standard, to the CCSDS standard, for which we have been invited to participate and help them sort out this security issue. And then we are also going to add some new functionalities to the exploit we have developed, and at some point, most likely we're going to open source it once those issues have been resolved, probably at the CCSDS level. As I said, all what you have seen is a public knowledge. Here is a full list of references you can have a look at, which is also in the publication, which you can find here on this link, so you can capture it and have a look later. Here is also some further research we have done on the space-related systems, both on the ground and on the spacecraft onboard software. You probably won't, if you are interested, I can give you the links later, or maybe once you have access to the presentations. And that was the last slide. Thank you very much. Are there any questions? So the question is, what's the reason why SLE is not encrypted, which leads to all those attacks? The main reason is probably legacy. The standard came out quite some time ago, where people were not really thinking about encryption. And there is also, at least in space industry, I have the feeling that there is that notion that if it's internally in the network, it's not going to be accessible by people from outside. So, as you know, that's not the truth. Usually what happens is you get access to the system, to a system through the publicly facing website, and then you get access to the internal network. Once you have access to internal network, you can start doing what we have done. But that's not, that's really not how people in space industry see it. They hide behind the firewall, they set up VPN, and they think that's, okay, I should probably not generalize, but we all have seen what happened to Viasat when the war started in Ukraine, right? So it was because of the legacy systems, because of lack of encryption. The onboard software was uploaded to spacecraft through the plain FTP protocol, and the only security measure they had was a VPN, which adversaries breach in no time, basically figuring out what the credentials are. So obviously that was a mistake, but it is still happening. So the ground station.
So the other aspect is the ground station to the satellite communication. So now you're free space. So you're open to anybody, there's no man in the middle or even the device, and back-end traps people can get in. That's one. Secondly, we are talking about post-quantum cryptography in these days and time. So, and you are just operating on bare bone, no encryption. So is this like the standard that space agencies use worldwide?
I cannot speak about military solutions, but if you think about it, you have a spacecraft which was launched 10 years ago, or 15, or maybe 20 years ago. There is no security measures in those systems. So even if you try to encrypt communication at the ground segment, the spacecraft will not understand because you would have to, well, it depends really on the spacecraft because there might be some possibilities to patch the onboard software. But I've seen many missions which was basically impossible to patch onboard software already, let alone add additional requirements for encryption and for processing of that encryption because there is not enough power at the spacecraft. So this is one of the reasons this happens is because these are really legacy systems.
What about the newer satellites that are being launched?
So as one of the slides as I showed before, CCSDS came up with the Space Data Link Security Protocol, which is on the link between the ground station and the spacecraft. So that is going to be secured. However, the link between the mission control system and the ground segment is not secured, which means that if you start injecting telecommands on the link between the mission control system and the ground segment, your commands are going to be encrypted and will go to spacecraft anyway for the execution. So you are conducting an attack before the commands are encrypted.
And these new standards being suggested, are they going to be post-quantum secure also?
No, they are not.
Thank you.
So I have a question. This was one we were kind of discussing last night. We know that a lot of the space systems use very legacy code. NASA's still using stuff from the Apollo program. Obviously, we weren't worried about security then. And a lot of these systems are 10, 20, 30, 40 years old. In addition, we also have a similar concept within the medical device industry to where, say, that we can't update MRIs. They're still running Windows 98 because that's the software that they're based on. How do we go about securing legacy systems in a modern world, whether it's with the space agencies, medical systems, other critical infrastructure with dams that we really can't update? They don't have enough power on that end. We never designed it in the first place to deal with that. What's your thoughts on protecting our our systems that are legacy that we can't update against modern threats?
Yeah, that's a good question. So I have some thoughts about it because obviously you cannot make sure that all your systems are secured. But what I have seen in the industry, what is happening, as I said before, people are hiding behind the firewall and behind the VPN, and they call it end-to-end security. And sometimes they even call it zero trust. So the issue is that you should, obviously you will not be able to make every single element of a space mission secure, but you should break it down into pieces and try to make secure those elements which you can. One of those elements is SLE. You should try to make it secure. You should try to make secure the mission control systems because these are the most critical systems, and they are systems which are not really legacy because they are developed on a day-to-day basis, and every mission has a new system. However, they are so critical because they are the only systems that are used by the people. And as we know, people are the weakest link in any information system. So you have to make sure that these are secured, right? So you have to take the mission, break it into pieces, and grab the elements which you can make secure, and then you have to secure those. There will be things running on Windows 85. There will be things running on something which is not even Windows, or before Windows. Those, of course, you cannot make secure, but you can make secure all the communication and bits and pieces around. And the reason why this is better than hiding behind the firewall or VPN is because once the adversaries, like in case of Viasat, they breach the VPN securities, then they will be able to tear your mission apart, basically. And that's because all those elements are not secured. So I think that's the best approach.
Sir, from students' point of view, like Sir said that in critical infrastructures, we have many protocols which are insecure by design. If we talk about ICS, we have Modbus. If we talk about drones, so we have Mavlink, which are proven to be where such attacks have happened. So we are learning using different simulators, like ICS simulator we have if you want to learn about Modbus security. And for drone, we have other software. So anything about if you want to start into satellite hacking and about this?
Sorry, I didn't get the question.
So anything if from a student's point of view, if I want to learn or simulate these things at my end for learning point of view, so what can I do? Like,
sorry, I didn't get the question. I don't understand.
Yes. So basically, he's trying to ask, like, is there any simulator to start practicing these exploits? Any lab environment for this? For students or newcomers?
Oh, how are we going to do this in practice?
Yes, for practice, yes.
Well, this was the practice. What you have seen was actually this is not academic. This is exactly the software which we use it for testing. It is the software that is used at the ground station and at the mission control. So that's exactly what you saw. That's exactly how you would do. So the thing is that, as I said before, this is assumed breach testing scenario. So the assumption is that you are an adversary and you are in the network already. Let's say you bypass the firewall, you maybe hacked one of the front-facing website, you are in the network, and so then what you do, you have access to the software which you have seen. The software might be a little bit different depending on the organization, but as I said, this is implementation independent because the software has to follow the standard, the communication standard. And so every implementation is going to behave in the same way. And therefore, if you are doing the man-in-the-middle attack, you can, it's software agnostic. You can just do exactly the same at any mission control system to ground station link that uses SLE.
Okay, thank you.
Hey, morning. So I do have one question that you have shown the example of different headers in decoding a request. So there were a bunch of headers. So I would like to ask you that how do an application or the protocol, yeah, that's right. So how do we identify that which header is ending when or which is starting the next header?
So, excuse me. Some of it is in the documentation. Mm-hmm. And then ISP1 is based on ASN1 notation encoding. So we just follow the same well-defined structure of tag field and value, right? Tag length value, TLV.
Okay, so do they have a certain length, character length or something?
Sorry, I didn't get that.
Do they have certain character length or a certain header? Like the first header is ISP1 header, so is that any certain particular character length for that?
Yeah.
Okay.
So as I said, it's a typical TLV. So you have a tag which defines the element, the beginning of the element. Then you have the length of that element, and then you have the actual value. So there are some elements which are not typical TLV, but they are described in the standard, which are as a custom sequences and custom context-related structures. But they are described with a fixed tag, which you can easily identify, and then you just apply the length, and then you grab the value from those from that byte string.
Okay, thank you.
Yeah, hi. It's kind of a dumb question, but I think I wanted to ask if recently Apple launched satellite communication with the phones, right? So is it any kind of similar protocol or communication that it is using? Or is it possible to intercept those kind of messages and then manipulate them?
You mean at the ground to spacecraft or at the ground segment?
No, the iPhones, the iPhone 14 series and later, they can, in the emergency situation where there is no network communication, they can contact with satellites and then send emergency calls and messages. So is that in any kind of way similar to what you have shown here?
I think I don't understand the question. Can you maybe rephrase it? Because
iPhones in the recent days can connect to satellites and send messages, as Apple claims. I have not tested it and I don't have much knowledge about it, but it is using some kind of technology to connect to satellites and send emergency calls and messages to services of police and ambulance, etc. So I'm curious about the protocol that it is using and if it is able, if anyone is able to manipulate it.
Yeah, honestly, I'm not sure how this is done. I'm not aware how the infrastructure of that communication is developed or is put in place. So there is, even though that you are communicating with your phone to a system, it is quite likely that it's going to be encrypted at the communication between your phone and the system. But then internally in the network, it's not going to be encrypted, and that's probably it's very likely because of the legacy issues. Because all that communication, the systems, the protocol is not secure, and if they are using this protocol, the encryption internally in the network will definitely not be. The communication in the network will definitely not be encrypted. So the communication between your phone and the ground system might be secure. But then it's going to be unencrypted, and then it's going to be sent in a plain format to the ground station, and then it's going to be uplinked to the spacecraft. The uplink to the spacecraft might be secure. It depends on the implementation. But if it's done using SLE on the ground station site, it's not going to be encrypted.
Thank you.
No more questions. Okay. Okay. Thank you very much again. I hope you enjoyed it.